tectonic activity on Earth is constantly creating these deformations of the Earth's crust. And we'll see these stratifying layers. And that's just due to material in the mantle pushing and shifting the crust, causing them to rise or slide or rip apart. So all of these processes are powered by the heat underneath the Earth's surface, and the bulk of that heat or energy is generated by radioactive elements in the core and the mantle just decaying away. As they decay, it generates a lot of heat. So we can break Earth's crust into these lithospheric plates, and we can talk about consequences of continental drift or the plate tectonics. That describes the motion of these lithospheric plates. Now, Earth's crust can be broken up into 7 major plates and 6 smaller ones, and what dictates their motion is mostly convection. You can think of convection as take your boiling water, and the hotter materials, the hotter gas, is going to start rising while the colder falls. Well, same thing can happen with the mantle. All right, mantle's getting heated from below due to the radioactive material underneath, and this causes some pressure changes. The heat will try to push up, raising materials and creating this separation. This material will push upwards, and you'll have these streams of these plates that slide outwards. Now, a wonderful way for us to actually witness and see that these plates are shifting out is actually a property of Earth's flipping magnetic field. Now, how we understand Earth's field is flipping around is an entirely separate video on its own. But for now, we'll stick with we understand that every so often Earth's magnetic field will change orientation. So what's happening? Go to about 4 million years ago. Hard material is rising, and take these 2 plates, and they're going to be this pushing, this separation. So this material is an Earth's magnetic field oriented one direction, and the shifting of the plates is driving them apart. Well, go about 1 million years later, and Earth's magnetic field has shifted around, rotated. And now we have these inverted poles, and the material is still going outwards. Go for another 2 million years. Right? Poles flipped again, push the material out. Keep going. Material is getting pushed upwards, and the fields are rotating. So we'll see these bands of field one direction, then another, then flip again. And this pattern of flipping tells us how quickly these plates are separating over millions of years. Now, depending where on the Earth these plates are moving, you'll have some plates that are separating, they're going apart, and other places where they're pinching, coming in together due to the other forces pushing and straining on them. So, across the planet, we'll see that the majority of volcanoes that you can find and where earthquakes will be found follow these plates. So black dots correspond to high frequency of earthquakes, and the white dots are where you're going to find volcanoes around the planet. So we have all sorts of geological records to convince ourselves that Earth has tectonic plates, but what about other planets? Well, we pretty certain Mars has tectonic plates. Mercury is a very fascinating example. If you look at the surface of Mercury, so here's a zoom in on Mercury, and you see what we call scarps, basically a high ridge region that suddenly collapses down. What we suspect happened is that the surface of Mercury shrank as it got cooled. As it was radiating its thermal energy away, it started shrinking down. But Mercury was then being heated up by the sun, and that created what we call this kind of wrinkle effect. Basically a raisin, right? A wrinkled grape, creating these harsh scarped surfaces on the surface of Mercury. So we're not entirely certain if there's tectonic plates on Mercury, but we see these fascinating regions on its surface due to this problem of cooling and heating by multiple sources. Mars has this fascinating feature called the Valles Marineris, shown here with a little depiction of the United States of America sketched over it. This thing is gigantic. If you want to put a name to it, you can call it the Super Grand Canyon. This thing is about 3,000 kilometers wide, and on average, the depths will change, some of it going very deep, but on average, across this whole thing, it's about 8 kilometers just deep. Now, coming over to Venus, we suspect there's a different type of tectonism there, and it's a problem of this crust melting and bubbling over due to just the high temperatures on Venus. It's hard to tell because Venus's atmosphere is so thick that we had to find other ways to image that. So one example is this image here from the Magellan spacecraft that flew by and used radar imaging. Remember, radar is very good at passing through gases because it's long wavelengths. So using radar, we're able to get this idea of what the surface features look like, and we see these crazy banding patterns, which led us to believe in this concept of the melting of that crust turning over constantly. Related to tectonism is volcanism. Once again, think about this. You'll have hot spots. That's pushing material up through the layers of the crust. You'll have these regions, hot regions that can break through the crust. So tectonic plates movements, once again, is generated by thermal energy and friction. So you'll have these frictions, you'll have these hot spots, and that combination of heat with what we'll call convection cells in the mantle can create regions of magma that can spew forth in the volcanoes, hence our volcanism. Volcanoes most often form at the regions where you'll have hot spots, that boundary between mantles and plates, where very hot magma material can accumulate and through the pressures rupture through the surfaces. Now, we often think of volcanoes as being these big, massive explosions, but you have examples of what's called a shield volcano, where basically it's just a vent for material to ooze up and slide on down. So this is a hot magma just kind of bubbling forth and flowing downwards from gravity. This creates a smoothing effect. Remember, tectonism and volcanism was one of our examples that could smooth the features of the surface of a terrestrial planet. You also have examples of composite volcanoes, which are basically thick lava forms, and these can spew forth rapidly. Looking at volcanism on otherworldly objects, here's a picture of the Mare Imbrium on the moon, and you see what looks to be edges of previous lava flow. So the moon doesn't have any volcanoes, it's not very geologically active, but seeing smooth boundary like this tells us that at some point the moon was active enough geologically for that to be present. We can see similar patterns on Mercury, and we've even seen we imagine or we think are a few inactive volcanoes. Once again, the telltale sign is this smooth surfaces, smooth regions, because the smoothing is mostly being done in these pictures by volcanic material oozing up, flowing out, and cooling off. Now, Mars happens to have the largest volcanoes in the solar system, and these are a type of shield volcanoes. The biggest one being Olympus Mons, and here's a orbital picture of this thing. To put it in perspective, here is Olympus Mons, the giant shield volcano, and here is Mount Everest on Earth as a size comparison. Only about 12,000 meters bigger in size. Now, while Mars might have the biggest volcanoes, Venus will have the largest number of volcanoes. This image here is an image in the visible spectrum showing a false color, basically tweaking with the colors to highlight certain features. Each one of these gray spots corresponds to a volcano. Now remember, Venus is very hot, we believe to be very active, having all these regions of that crust constantly bubbling and turning over. The sheer number of volcanoes helps with that change.